All right, let's jump straight into this. If you are a brand new structural engineer, stepping into the world of American design codes can honestly feel like you've been dropped headfirst into a giant bowl of alphabet soup. You're hearing terms flying around the office: IBC, ASCE 7, ACI 318, AISC 360. And, it's a miracle anyone actually knows which book to open first. But don't worry, in this explainer, we're totally decoding this source material together. We are going to look at exactly how all these codes actually fit together so you can start designing with real confidence. So imagine you've just been handed this incredible project. We're talking a 10-story reinforced concrete office building out in California. Now, the ultimate trap for a new engineer, and this is a big one, is to immediately fire up that modeling software and just start assigning concrete grades. If you're doing that, you're really just operating software. True structural engineering, that requires actually understanding the underlying design basis first. Why? Because someone literally has to decide if that software model actually represents reality. And here is our exact roadmap for today. We'll hit the fresher trap, the code hierarchy, understanding IBC and ASCE 7, material codes, the load path, and finally, software versus judgment. By the end, these won't look like hundreds of unrelated documents anymore. Okay, starting right off with Section 1, the fresher trap. The guidance makes it absolutely clear that before you ever even touch a computer mouse, there are fundamental questions you have to answer. What is the adopted building code for your specific jurisdiction? What's the building's occupancy? What's the risk category? What about the seismic parameters for that exact piece of dirt you're building on? Figuring out which document controls which of these decisions, that is the actual job. The software comes much, much later. That brings us right to Section 2, the code ecosystem hierarchy. You see, the American code system isn't just one massive 1,000-page book you have to memorize. It is way more like an interconnected building with several levels, and you navigate it from the top down. It's a literal chain of decisions. You start with the overarching building code. That dictates your loads. Those loads drive your analysis. That analysis leads to your material design and finally, construction. The higher-level codes act just like a map, telling you exactly where to look next. Let's transition over to Section 3, where we'll look at the top two levels of our hierarchy, understanding IBC and ASCE 7. At the very top, running the whole show, we have the IBC, or the International Building Code. Think of the IBC as this giant umbrella that ties everything else together. It's not going to replace your material codes, right? You aren't going to find the exact formula for a concrete beam in here. Instead, it acts as the regulatory framework. It establishes your building's occupancy, construction type, and risk category. And then it legally mandates exactly which specific design standards you absolutely must use for the rest of your project. And honestly, one of the very first things the IBC will do is point you straight over to ASCE 7. This is the foundational load standard in the United States. ASCE 7 answers one really fundamental question. What loads and load combinations does my structure actually need to resist? Once the IBC sends us here, this is where we find all our highly specific load requirements and those critical LRFD or ASD load combinations. It's fascinating how ASCE 7 maps out all these distinct hazards for us. You've got your gravity loads on one side, stuff like dead, live, snow, and rain pushing down. Then, on the other side, you've got environmental loads, wind, earthquakes, even tsunamis. But here's the kicker. ASCE 7 doesn't just hand you the magnitude of these forces. It tells you exactly how they interact through really strict combination equations. Because, let's face it, out in the real world, forces basically never happen in a vacuum. Let's look at a really quick example to put that into perspective. Say you have a beam with a dead load of 12 kilonewtons per meter and a live load of 6 kilonewtons per meter. You don't just add 12 and 6 together and call it a day. You have to apply those ASCE 7 load combinations. So taking a standard 1.2 dead plus 1.6 live combination, that factors up to a design demand of 24 kilonewtons per meter. And that right there is the exact required strength your member needs to resist. Moving right along to Section 4, material codes and connections. Because now that we have our factored loads, we have to prove our materials can actually hold up. If you are designing in concrete, the IBC points you directly to ACI 318. This is the ultimate controlling standard for everything concrete. We're talking flexure and beams and slabs, punching shear and foundations, all the way to incredibly complex seismic detailing. ACI 318 is where you go to definitively answer, can this specific concrete structure safely resist the demands we just calculated back in ASCE 7? Now, if you are designing in steel, the IBC mandates AISC 360. This standard handles all your typical steel member design: tension, compression, lateral torsional buckling, the whole shebang. But wait, if you're designing a steel building in a high seismic zone, like our California office example from earlier, a completely separate standard called AISC 341 kicks in. That one provides all the special high seismic ductility rules you're going to need. But keep in mind, just designing a beam or a column, that's really only half the battle. Those forces have to travel safely through connections and alternate materials. And that is exactly why the IBC references this much wider alphabet soup of specialized standards. You've got AWC NDS for wood, TMS for masonry, AWS for welding. This massive interconnected web ensures that absolutely every single piece of your structure is legally governed by a specialized rule. All right, let's move to Section 5, the structural load path. This is arguably the absolute most important conceptual takeaway of this entire explainer: how structural forces actually physically travel. If a huge gust of wind hits a roof, that force doesn't just magically vanish, right? It hits the roof components, it travels into the framing, it moves into your bracing systems or diaphragms, transfers down the columns and walls, hits the foundation, and finally dissipates right into the soil. The overarching lesson here? Memorizing codes is practically useless if you can't vividly visualize this structural behavior in your mind's eye. And that brings us to our final section: software versus engineering judgment. Now, right before we dive into the software itself, the industry guidance warns of a seriously dangerous professional mistake. It's called the addition trap. You literally cannot just blindly mix code additions or just assume that whatever latest PDF you downloaded online is the correct one to use. You absolutely must always check what the authority having jurisdiction, your AHJ, has officially adopted for that specific project. Honestly, using a 2024 code with a 2014 material standard might be completely legally invalid in your city. So once you actually have your design criteria properly established, then and only then can you bring in the software. And look, whether you use ETABS for your modal analysis, SAP 2000 for something complex, or SAFE for your foundations, you have to remember one absolutely crucial thing. A beautiful, colorful, spinning 3D model does not automatically mean a structure is intelligently designed. The software simply calculates whatever you tell it to calculate. Just look at this progression roadmap. This is how you actually build a resilient career. First, you start with fundamental mechanics. Then, you master the code ecosystem we just talked about. Then you master your loads, your analysis, your materials. And finally, after all of that, you master the software. If you follow this specific workflow, you become incredibly adaptable. You'll be able to seamlessly transition to international environments like the Eurocodes simply because you understand the actual engineering mechanics, not just a bunch of memorized buttons on a screen. The sources leave us with this really powerful core philosophy, and it pretty much sums up everything we've looked at today. Software calculates, codes provide requirements, engineers make decisions. Software is strictly a tool to implement your engineering decisions. It is never, ever an excuse to replace them. So, as you head into your very next build, I really want to challenge you. Stop asking, what software should I use? And start asking the true engineering questions. Understand your loads, understand that critical load path, and most importantly, ask yourself what limit states actually matter most for your next project.